I'd like to tell you about a generalization of the Calabi problem for Kähler manifolds and the Hall-Strominger system for non-necessarily Kähler Calabi-Yau manifolds. We call it the Calabi system, and it is best understood through generalized geometry. In this talk, I will first recall the Calabi problem and the Hall-Strominger system in order to motivate and state very clearly the Calabi system. I will then give a crash course on generalized geometry and use it, the final part of the talk, to state our main results. All I am going to say is joint work with Mario García Fernández, Carl Tipler, and Carlos Shabazzi. Let me first fix some notation. X will be a compact complex manifold with a complex structure J, which will give a decomposition into PQ forms and a decomposition of the differential operator to del and del bar. G, a Hermitian metric, that is a Riemannian metric which is Q-symmetric with respect to J, will be usually denoted by the associated omega, the 1-1 form. A compact complex manifold with a Hermitian metric is Kähler when this 1-1 form is closed, and its cohomology class is the Kähler class. On the other hand, a compact complex manifold with a holomorphic volume form, which I denote by omega, capital Omega, will be a Calabi-Yau manifold. The Calabi problem appeared for the first time in 1954 in the Proceedings of the International Congress of Mathematicians of Amsterdam, and it appeared as a theorem. And it said that given a 1-1 form, cohomologous to 2 pi the first chain class, you can always find a unique Kähler metric whose Ricci tensor is this 1-1 form you started with. 3 years later, in 1957, it appeared again, now as a proposition, in some proceedings of a symposium in honor of Lefschetz. And if you look at the proof, there is a cross with a footnote. And this footnote said that this result, this proof, depended on the conjecture that a compact Kähler manifold admits a Kähler metric with any assigned positive differentiable volume element. So actually, the problem of Calabi was given a Kähler manifold and a smooth volume form. Can I find this Kähler metric, this Kähler form, such that its nth power will give me essentially this smooth volume form? This was solved 20 years later by Yau, who fixed the Kähler class and then solved the complex Monch-Ampere equation for the potential phi. So he proved essentially that given this Kähler manifold, given this smooth volume form, you can always find this Kähler metric, and that is also unique in its Kähler class. This was the Calabi problem. I would like to talk also about the Hall-Strominger system. This is a system of equations introduced around 1985-86 in string theory. It starts with a Calabi-Yau threefold and a vector bundle. And you want to find a conformally balanced metric. Conformally balanced means that multiplied by a function, it will be balanced, which means that omega to the power of n minus 1 will be closed. And together with this metric, you have to find two Hermite-Yang-Mills connections, one on your base manifold and another one on the bundle, and they have to be coupled in this way. So you must have this equation in 4 forms relating your Hermitian metric and the two connections. For our talk, I'm going to give a more precise version now of this Hall-Strominger system. We will fix a compactly group, and in its Lie algebra we will have a bivariant pairing. take the killing form if you wish. And I will take a Calabi-Yau manifold of any dimension and a principal K bundle. So the Hall-Strominger system is finding a Hermitian metric omega and a connection theta whose curvature I will denote by F, such that these four equations are satisfied. So the top line is Hermite-Yang-Mills. The third equation is this conformally balanced, but in a very precise way, with this norm, which you can see here what it exactly means. And finally, we have this Bianchi equation, this equation of four forms relating everything. Now that I've introduced this system, let me just motivate its study. It's not only coming from physics, it's also coming from math. In fact, Yau stated in a review about complex geometry and its present and its future that one should study for balanced manifolds the Hall-Strominger system. The system I'm going to talk about is a generalization of both the Calabi problem and the Hall-Strominger system. It's the Calabi system. In this system, we will consider a compact complex manifold with a smooth volume form and a principal K bundle for K compactly group, and also a real parameter. In this system, we have to find Hermitian metric and a connection satisfying these four equations here. Hermite-Yang-Mills, the conformally balanced equation, but now with more generality because my volume form is a smooth volume form, NFit, and the Bianchi identity. If you look at this system, you will see how we can recover both systems. Of course, it's very easy to see how we recover the Hall-Strominger system. You just have to take L equal to 1 and take the smooth volume form to be the volume form associated to capital omega, to the holomorphic volume form, and just adjusting a coefficient. It's more interesting to see how we can recover the Calabi problem. For this, I have to take L equals 1 and no bundle at all. If I do that, my system gets reduced to these two equations. The first one is a conformally balanced type condition, and the second one is DDC closed. So by a theorem of Ivanov and Papadopoulos, DDC closed and conformally balanced will give me that omega is in fact Kähler. Once I have that omega is Kähler, I go to the first equation and I can see that actually this F omega is constant. So now, since it's constant by the definition of this F omega, I will be able to rescale my omega in such a way that I will solve the Calabi problem. Since F omega is constant, by rescaling omega with F omega, it will still be closed as I need. So why I study the Calabi system? So in order to fully answer these questions, we first need to go into a crash course on generalized geometry. Okay, for the sake of simplicity, let me first talk about generalized geometry for smooth manifolds. So M will denote now a manifold, and if you think about it, geometry is usually done by using the tangent bundle of the manifold. So symplectic structures are two forms on this tangent bundle, and even things like a complex structure, which is a complex atlas with holomorphic changes of charts, is also given as an endomorphism of the tangent bundle squaring to minus the identity. Generalized geometry proposes changing a bit this mindset and considering the tangent plus the cotangent bundle. So, what happens to the classical structures we know? Imagine a presymplectic form on your manifold, just a closed-to form. So, if you want to regard it in this new generalized way, you should look at its graph, because its graph will be a sub-bundle of the sum Tm plus T star m. And if you have a Poisson bivector, you can do the same. Its graph, when you look at it as a map from T star m to Tm, will be again a sub-bundle of Tm plus T star m. On the other hand, you can consider a complex structure, which was an endomorphism of Tm. You can consider its dual endomorphism, which will be an endomorphism of the cotangent bundle, and put them into this matrix, and you've obtained an endomorphism of Tm plus T star m, and because of this choice of sign, we will have that it squares to minus identity. If we have a symplectic form now, closed but also non-degenerate, can also fit it into one of these matrices, because we can take the inverse of the symplectic form, when I see it as a map from Tm to T star m, and put it together with the symplectic form in the off-diagonal entries, and I will get again this endomorphism of tangent plus cotangent squaring to minus identity. So many classical structures can be regarded inside this Tm plus T star m. The interesting thing is that Tm plus T star m is not any bundle. It has a pairing. I know how to evaluate one form in a vector. So it has some more structure. So this pairing, where I denote a section of Tm plus T star m by V plus Xi or W plus eta, come with this pairing, and what happens to the objects I have defined. So the objects on the left-hand side turn to be maximally isotropic as sub-bundles for this pairing. Note that this pairing is split. It has signature NN. Whereas on the right-hand side, what I get are skew-symmetric endomorphisms for this pairing. This is nice, because first I could see my structures just inside bundles, but now I have this additional structure of a pairing, but it doesn't end here, because this is actually something that happens at every point. There's some geometry going on. There is a bracket on sections of Tn plus T star m. This is the Dorfman bracket. So this bracket reads like this. So it has to give me a vector plus a one form. The vector field part is the Lie bracket, whereas the one form is defined using the Lie derivative and the differential operator. When I consider these structures I had before with this Dorfman bracket, it turns out that the subbundles I had on the left-hand side that were maximally isotropic, they are also involutive for this Dorfman bracket. Whereas the endomorphisms of the right, when I complexify them and I look at its plus I eigenspace, they have also a plus I eigenbundle, which is involutive. What we have on the left-hand side are Dirac structures, as introduced by Courant and Weinstein, and they describe mechanical systems that have both constraints and symmetries. This is why they came up. On the right-hand side, we have generalized complex structures. There are structures strictly between almost complex and complex structures, and also give a natural language for other structures or phenomena, for instance, bi-Hermitian structures or some extended complex deformations become very natural in the language of deformation of generalized complex structures, as it was introduced and developed by Hitchin, Gualtieri, and Cavalcanti. If you look at this bracket, you may notice something is not quite skew-symmetric. I didn't say it was skew-symmetric, so it's bilinear. And what happens when I do the bracket of an element with itself? So I'm getting something which is not zero. The vector is zero, but I get a one form. But this one form is actually the differential of the norm square, if you want, of this generalized vector field. It is not skew-symmetric, but it satisfies very nice properties. It still satisfies some kind of Jacobi identity. I say some kind because it's not skew-symmetric, so you wouldn't be able to put it as a cyclical Jacobi identity. You can either put it in this way, which is nicer, which is the bracket by a section is a derivation of the bracket itself. And this is what happens also with respect to the pairing. When I act on the pairing of two elements, in this case, I take my generalized vector field, this vector plus one form, and I project onto the vector field part, and I act on this pairing, it turns out that it also acts as a derivation. And actually, this structure has a name. The name is current algebroid. So what's a current algebroid? I will talk just about the general definition briefly. So it's going to be a vector bundle over a manifold M together with a non-degenerate symmetric pairing, linear bracket, and a bundle map. This is called the anchor map. This before was only just the projection from Tm plus T star M to Tm. And the properties that has to satisfy can be summarized in these two. That the bracket by an element has to be a derivation of both the bracket and the pairing. And then there is no skew-symmetric, but we know what's the discrepancy to this non-skew-symmetry. If you look around, you will see there are 5 properties sometimes, okay? But 2 of them are a consequence of these 3, which I put here as 2. Example of this, so we have one. We have Tm plus T star M with the pairing and the bracket, but we can, for any closed 3 form, we can twist the bracket while keeping the pairing and the projection the same. This twisting, what we do is we add an extra term for the one form. This extra term is Ix, Iy, H. And this tuple is a current algebroid. Current algebroids have natural transformations that preserve all this structure. So the automorphism group will be just these bundle maps from the bundle to itself, which have to cover a diffeomorphism, and they must satisfy as compatibility conditions with the 3 objects we have: pairing, bracket, this anchor map. Not every automorphism of a current algebroid comes necessarily from a diffeomorphism. So we can see here how any diffeomorphism will give me an automorphism of the current algebroid, but I also have, for any closed to form, this B-field transformation, which is taking a generalized vector field V plus Xc to V plus Xc plus the evaluation of V on the 2 form B. And actually, these are essentially the automorphisms of Tm plus T star M with the current, the Dorfman bracket, the current structure I introduced. And the group of automorphisms, or sometimes called generalized diffeomorphisms, is actually the semi-direct product of diffeomorphisms and 2 forms. I'm going to move now to exact current algebroids. So notice that for any current algebroid, since I have this pi, this projection to Tm, I have its dual that would go into E dual, but with a pairing it goes into E. And if this sequence is exact, then I call it an exact current algebroid. And there is a way of classifying all possible exact current algebroids up to equivalence. And what you do is actually notice that, well, as a vector bundle, E will be the sum of Tm plus T star M, just by taking a splitting. But you can take a splitting in such a way that the image is isotropic. So when you do that, what you get is this isomorphism that preserves the pairing and the anchor map. Okay? But what happens to the bracket? So the bracket of E, when you see it in Tm plus T star M, will be the bracket that is given by some closed three-form H. What happens if you take a different isotropic splitting is that you would get a different isomorphism to a different courant algebra, but the three-form differs by an exact three-form. So it's a closed form, and up to exact three-form, that's the cohomology. And this is actually the Chevera class of an exact courant algebra. Let me move now to holomorphic courant algebras. So this was the definition of a courant algebra, and now I want to do it holomorphic. So what do? I change the notation. I will, instead of E and M, will use Q for the holomorphic bundle and X as before for the complex manifold. So here I have it. A holomorphic courant algebra will be a vector bundle which will be holomorphic over a complex manifold. The pairing, the bracket, will be holomorphic. Here the bracket, I'm putting it on the sheaf of holomorphic sections in case they are defined just locally. The bundle map has to be holomorphic, and then I have the same two properties. We will be focusing on a large class of courant algebras for which the anchor map is surjective. This means that the courant algebra is transitive. This is how we call it. And in this case, we have actually associated to our holomorphic courant algebra a holomorphic Lie algebra by doing this quotient by the orthogonal of the kernel of the anchor map, and a holomorphic bundle of quadratic Lie algebras by taking this as a bundle actually of this AQ that are naturally associated to any transitive holomorphic courant algebra. So having a holomorphic Lie algebra and inside of it a holomorphic bundle of quadratic Lie algebras reminds us of Atiyah Lie algebras, holomorphic Atiyah Lie algebras. So the class of holomorphic courant algebras we are interested in are called string algebras, and are the ones for which these two bundles I can associate actually are isomorphic to the ones coming from a holomorphic Atiyah Lie algebra. To define that object, the only thing I need is a holomorphic principal G bundle. So this is my string algebra definition. And now let me give you an example of this. How does it look? So you can take any quadratic Lie algebra and you can put in here T, holomorphic dual of Tx, and you consider X times this Lie algebra. The anchor map is just a projection to T, and the pairing is the one you define using the pairing of vectors and one forms and the pairing of the Lie algebra, and the bracket you can combine everything here. Okay, so look, there are some terms that are really similar to the ones I had before. Okay, this is kind of the Lie derivative but with the del operator, and here I have this other term was also around, but now I also have a term coming from the bracket. I also have some more interaction between this new component in the middle. R and T, okay, are sections of this trivial G bundle over X. One of our first results that is crucial to this talk is the classification of string algebras. Before, we classified exact courant algebras by cohomology classes. Here, I'm not going to get into the equivalence so much, but I'm going to tell what are the objects that appear. So there is a principal bundle, there is a 3 form, but it's of type 3, 0 plus 2, 1, and there is a connection on your principal bundle, and they have to satisfy this identity, which is extremely similar to the Bianchi identity we saw in the Halley-Strominger system and in our Calabi system. So any string algebroid will be isomorphic to one which is tangent plus cotangent, holomorphic, and the adjoint bundle of your principal bundle. And the holomorphic structure and bracket pairing, everything will be determined by your data h and theta. Okay, p is already there in the middle. How it is determined? Okay, I can show it to you. Yes, so that we know we have it, but I won't use it. So this is how the Dolbeau operator, the holomorphic structure, looks, and the bracket is a bit like the one I showed you before, but a bit more complicated. So this is it now with the twisted with the 3 form. Note that there is actually here a very similar term to the one we had before. I added when I twisted the bracket by h. So apart from holomorphic string algebroids, we can also define complex string algebroids and real string algebroids. And the ingredients, when we do the classification, will be the same. Will be equivalence classes, I don't enter into details of this equivalence, of a bundle, a 3 form, and a connection on the bundle. So on the left hand side, I have the holomorphic case, which I talked about. Holomorphic bundle, 3, 0 plus 2, 1 form, and connection. Okay, I will denote these objects usually by Q. When I have a complex version of this, so I have a complex bundle, H will be a complex 3 form, and I have a connection on my complex principal bundle, and these objects I will denote it by E, and they are all, what I put here in this line in the middle is that you can always find an isomorphism with one of these where the bracket and the complex structure is determined by H and theta. Okay, well, in this case, no complex structure, in this case, the bracket. And finally, we have the real version of this, and in this real version, we start with a compact principal bundle, real 3 form, and a connection on that principal bundle, and the same. I could do the same definition, I could classify them. When I classify them, I see they are isomorphic to this one here, tangent plus cotangent, and the adjoint bundle of the principal bundle, and the bracket is given by H and theta. So in this picture, holomorphic, complex, and compact, I have that I can forget the holomorphic structure of a string algebroid and produce a complex string algebroid. This is forgetful functor say. So in terms of classes, of equivalence classes, just a map giving me for any class of holomorphic a class of complex string. And I have another operation which is given any real string algebroid, I can complexify it and get a complex string algebroid. Not every string algebroid, holomorphic, when I don't say anything, okay, will be necessarily coming or having a real form, compact real form of its complexification, this special class of string algebroids. So these are called Bot-Chern algebroids. Okay, holomorphic such that the complex one admits a compact form. Yeah? So we prove that actually that compact form is unique at equivalence. So we have a map going from holomorphic to compact. What we prove with this is a chain correspondence. So in the same way as in the classical chain correspondence, here when I have a string algebroid, something holomorphic, okay, with an underlying complex string algebroid, so anytime I reduce this complex string algebroid to a real one, to a compact form, it's like taking a metric, that will determine what's called a horizontal lift. We're going to think about them as connections. Okay? So holomorphic object, any metric on the complex one defines a horizontal lift, a connection on this reduction. And the interesting thing is that connections for these objects are given by Hermitian metrics and connections. And these are precisely the unknowns of the Calabi system. Okay? This omega will have to be positive, and what we can do in the space of possible connections, if you want possible omega theta, is to define a functional in this way, and also a symplectic structure by just taking minus djd, the log of the functional. And it turns out that the space of positive connections, it has an action of the automorphisms of the string algebroid, and those automorphisms are not any, are the Hamiltonian automorphisms. If you remember, in our Calabi system, we had compact complex X and my principal bundle pk, and this was the Calabi system, Hermite-Yang-Mills connection, this very precise conformally balanced condition, and the Bianchi identity. So now, each solution of this system, omega theta, I've said that it is actually a connection of some other object, of a real string algebroid. And there is a way of, if you are now still thinking about, okay, for a real string algebroid, I need a principal K bundle, I need a connection, and I need H. So here we have the principal bundle, we have the connection. Where is H? So H is precisely DC omega. So each solution of the Calabi system, I can see it as a horizontal lift, as a connection of this real string algebroid. Okay. Now what we do is we take all the solutions and we look at all the solutions of this system that correspond to the same real string algebroid. So what we prove is that those correspond to the zeros of the moment map of the action I mentioned before. So, for a string algebroid, I have its space of connections where I have an action by Hamiltonian automorphisms. We define a moment map for this action, and it turns out that the zeros of this moment map are precisely the solutions, are solutions of the Calabi system. Okay? I will recover the solutions associated to this real string algebroid. So, in particular, since the Calabi system has the power to recover the Hall-Strominger system, we are giving a moment map interpretation of the Hall-Strominger system. Thanks to this, by symplectic reduction, we can put on the space of solutions for the same fixed real string algebroid, we can define a symplectic structure. And also, assuming a technical condition, from a pseudo-Kähler metric, we can define on the space of connections. After doing also this symplectic reduction, we can obtain a pseudo-Kähler metric on this tangent space of solutions to the Calabi system for a fixed string algebroid. Of course, there's a thing I'm somehow hiding just to keep things simple, and it's about the symmetries of the theory. So, yeah, I will say like this: automorphism of string algebroids act on solutions to the Calabi system, okay, in such a way that this equivalence, I have now, if I have this equivalence of string algebras, this will give me some solutions also in the orbit, so I can quotient by this action when I want to look at the modular space. Actually, this invariance of the solutions to the Halley-Strominger system by some automorphisms in generalized geometry was our starting point. It was what made us think about using generalized geometry to best understand the Halley-Strominger system, and somehow when we were doing that we realized there was a better picture for that. So we went bigger, if you want, in order to see better the geometry. So the Calabi system allows us to see better how all these string classes appear in the Halley-Strominger system. At that point, we also proved this other theorem, which is that the Halley-Strominger system can be regarded as killing spinor equations in generalized geometry. And this, by the way, has been used very recently to produce the first examples of 0-2 mirror symmetry on compact non-Kähler complex manifolds. Finally, what I've done with the Calabi system has been, okay, you take a solution of this system, that solution lives in a class of solutions, which are the ones sharing the same real string algebra. Okay? Each solution determines a real string algebra. So, each of them, if you think about it, okay, this real string algebra, a solution is a connection on this real string algebra. And I said that a connection on this real string algebra, by the chain correspondence I stated before, will give me a holomorphic structure on the bundle, on allomorphic string algebra structure. So, all the solutions in a real string class will go into different holomorphic string classes. Now the question is, okay, how somehow up to equivalence, can two solutions here go to the same holomorphic class? Can I say something about this further division of solutions in a real string class? So in order to do that, what we can do is to fix the holomorphic string algebra and look at the solutions I can get for that fixed holomorphic string algebra. And we don't know it yet, but in a very simple but promising case, we found that actually there is uniqueness in a cohomological object in the Epley classes of that holomorphic string algebra. This is a very small case, complex surface with no bundle, but in that case the solutions of the Calabi system are parametrized by the Epley classes, this cohomological quantity of the string algebra. So uniqueness, we conjecture it depends on being on this cohomological class, and for the existence we're expecting to get some kind of, we think it would be best understood in terms of a stability condition. So let me summarize the talk in 1 minute. So on one hand, we have this well understood Calabi problem for Kähler manifolds. And on the other hand, you have this still mysterious Halley-Strominger system for non-Kähler Calabi-Yau manifolds. They both fit together into this Calabi system for compact complex manifolds. So this system is best understood through generalized geometry because its solutions fit into natural geometric objects. They fit into these real string classes, and each real string, each solution fits also in a holomorphic string class. Okay? In such a way that the space of solutions is the space of connections of a real string algebra, and that space of connections has a Hamiltonian action with a moment map and the zeros of the moment map are the solutions to the Calabi system. And if we go further, if we fix the holomorphic string algebroid, we've seen that in this very simple case, the solutions to the system are parametrized by apply classes. Thank you very much for your attention.